Thank you. Okay, good morning, everybody. Today I will talk about Noether currents for Eulerian variational principle in non-barotropic magnetohydrodynamics. And I will try to connect those Noether currents to topological conservation laws. So there will be a short introduction to those of you who are not familiar with MHD. There will be Eulerian variational principles and their topological constants of motion, and there will be Lagrangian variational principle and their topological constant of motion. And if we have time, we will talk about the stationary variational principle. Okay. So MHD is a problem in which we try to find what are the magnetic field B, the velocity field V, a density rho, and a specific entropy S, which are a total of 8 functions. And then we have all kinds of auxiliary quantities. In MHD J, the electric current is curl B. We don't have displacement current, and a pressure is a function of density and specific entropy. And this is the case of a non-barotropic flow. It's the more general case. In the barotropic case, we just have P as a function of rho. Those are the equations. We have 7 equations. Div B equals 0 is automatic from the first equation if it is satisfied initially. And then we have this equation for the entropy, which just tells us that the entropy in ideal flow is co-moving. And this means that we only take into account convection processes, but not conduction and not viscosity and many other things. Okay, so what is the content? Div B equals 0. We have a total magnetic field flux into a closed volume is null. What comes in comes out. As that the magnetic field lines are co-moving, they move with the flow, and this is, of course, very important for topology. And where does this equation come from? Well, we assume an Ohm's law, and we also assume that J over sigma is very small, so E is minus V cross B, and then you plug it into Faraday's law, which you know from electromagnetism, and you get this equation. Mass is conserved, and this is just Euler equation, which is Newton's second law for a continuous matter moving under the influence of pressure and magnetic forces. This we already discussed. No viscosity, no resistivity, so heat is just convected. Eulerian variational principles. So I'm going to pose some questions. One is, can those equations be derived from a variational principle? Can I do something to reduce the complexity, the number of functions? Can the number of functions describing the problem be reduced? And once we obtain a variational principle, what type of conservation's law can we obtain through Noether theorem, etc.? So this is a subject to a very long list of papers, starting from a paper with Linden Bell at 2008, and which involved only barotropic flows, and many others. I just mentioned them because I'm not going to give all the details in a presentation talk. It's impossible, but if you want to find the details, they are there. So, yeah. Two last one is with Hong King, 221, and another one from the same year. Okay. Now, the idea here is to look at magnetic field lines as an intersection of two surfaces. And this is, of course, restrictive because it means that the magnetic field lines move on surfaces. They can cover the surface, but they cannot cover a volume. So this is a very special kind of topology. But because they are co-moving, you can use the surfaces, which I call chi and eta, to have labels, coordinates of moving fluid elements. And then the only thing you need is the third one, which I'll discuss in more detail later, called the magnetic metage. It's a label going along the magnetic field line. So if you do the mathematics, you can show that you can write B as grad chi cross grad eta, and those surfaces will be co-moving. So this is a kind of economy because you replace those equations that you had initially, the natural equation, with just those two equations, and this is less equations. So how can we use those ideas in a variational principle? So here is our action, and we have a Lagrangian density made out of two pieces. One is very standard, kinetic energy, internal energy, magnetic energy, and one is a bunch of Lagrange multiplier, which are enforcing many things. Okay. So this part is well known, kinetic energy and pressure and entropy. Pressure is given in terms of internal energy. What do we enforce with the second part? The equation of continuity, the existence of two co-moving surfaces, conservation of entropy, and the fact that the magnetic field lines will enforce them to be at this intersection of two surfaces. So if you take a variation with respect to Lagrange variables, it's not a big surprise that you get those equations because this is built this way. And the same thing goes here. This is a Sakurai representation or Euler representation, whatever you prefer. And here is something a little bit new. If you take a variation with respect to the velocity comes out in this form. And this is, to those of you familiar with fluid dynamics, this is like a Clebsch representation, but it's more generalized. Chi, eta, and S appear here, and you have a scalar function, this nu. So this is the variation with respect to the density. It's a Bernoulli type equation. W here is a specific enthalpy. And variation with respect to the entropy results in this sigma equation, meaning that the sigma, the material derivative of sigma, is the temperature. And this is a variation with respect to chi and eta. You have a material derivative for alpha and beta. They are both dependent in some way on the current. Okay. So how are those related to the physical equations? Those are just variational equations. Those we already discussed. These are just the surfaces which the intersection is the magnetic field lines. And mass conservation, nothing to say about it. What about Euler equation? Do we get Euler equation? Well, if you take the Clebsch form and you make a material derivative, and then you plug in all the material derivatives of the relevant functions appearing here, it's just a few lines to show that the Euler equations are indeed satisfied. So this is just another form to represent the MHD problem. We have all the equations. Okay. So what we can say? We can say that we succeeded in deriving a variational principle for magnetohydrodynamics of the specific topology, of course. And then the variational equation contains the 8 physical variables and additional auxiliary variables. So we have 14 functions, and this is not very attractive. So what do? We rearrange the terms in the Lagrangian in the following form. We take all the terms which contain B and put them in one term, all the terms containing B in one term, and all the rest in L hat. And this is L hat, LV, and LB, and there is something going on in the boundary as well. V hat is just the Clebsch representation, and B hat is the Sakurai representation. So essentially, what you see is that those just give you the fact that V is in a Clebsch representation and B is in a Sakurai representation. We can assume that this in advance. We don't have to get it from a variational principle. And then we are left with the following. We remove those two terms, and we are left with the L hat. So now we have this Lagrangian, which is, of course, contains much less functions to play with. And those are the equations we get, and we know already that they are equivalent to the standard set of magnetohydrodynamic equations. Now, what I would like to point out is that this is not surprise, right? If you look at just standard electromagnetic theory, and you want to write a variational principle for it, the Lagrangian density, you must do it in terms of potentials. And this is the same thing here. We have potentials, and that's the best way to do a variational principle, also in the non-barotropic magnetohydrodynamics case. So now we have just a variational principle in terms of just 8 variables, which seems to be the correct number. But I would like to still pose a question: can one reduce the number of functions further? And the answer is probably yes, because if it was not yes, I would not ask this question. So let's look at those co-moving quantities, chi, eta, and s, and write them in terms where the velocity is written in terms of the Clebsch representation. So this is the form. And we can view those 3 equations as equation for 3 variables, alpha, beta, and sigma, right? So let's define a vector alpha, beta, and sigma, call it alpha I, and define another vector, chi, eta, and s, call it chi I, and then you have this ki. So if you write it in this form, those equations just take the form ki equals alpha j times grad chi dot grad chi j. And you define a symmetric matrix, aij, in terms of those co-moving labels, and you have this equation. And you can invert this matrix, and you can write the alpha j in terms of ki in this form. This is the just inversion of the matrix. And the velocity, if you plug those things in, will take this form. So now you have a Lagrangian density, which has only 5 functions. And these are the chi i's, nu, and rho. And this is the form of this Lagrangian density. And you can write it more explicitly, just putting the alpha I back in this form. So this is a bit complicated with the AJN minus 1, but it's correct. And it contains only 5 functions in explicit way. And if you do the Lagrangian, the variational analysis, those are the equations you have. And of course, by construction, chi, eta, and s are common. Now, if you are in the business of Hamiltonians, Casimir, Poisson brackets, etc., you may want to put it in a Hamiltonian form. So you can define the momenta, the canonical momenta in the standard way. And this is the definition of the canonical momenta. And you put it back, you calculate the Hamiltonian density in the standard way, and you will not be surprised that this Hamiltonian is just the energy density of the flow. And all the equations can be written as Hamiltonian equations in this form. So here and here. Okay. So it is shown that non-barotropic magnetohydrodynamics can be derived from a variational principle of 5 functions. In addition to the density and entropy, we have 2 surfaces on which the magnetic field lines lie, and an additional Bernoulli type equation. Hamiltonian and Lagrangian density are given in terms of the above quantities. Now, let's talk a little bit about topological constants. Cross-helicity was, I think, first in those 2 papers of Volger in 1958. And it characterized the degree of knottiness, twists, and many topological things that happen between the magnetic field line and the velocity lines. Unfortunately, cross-helicity is not conserved for non-barotropic MHD, because when you do the derivative, you find that it's equal to T grad S, should be a small s, is a specific entropy dot B, and this is usually not null. Or there is no reason to think that it should be null always, unless the flow is barotropic. So a question is, what is the analogous topological conserved quantity in non-barotropic MHD? Because it's not this. And the answer is that this can be determined from the variational equation. I will show you how, and this is connected to the first talk of this conference given by Renzo on non-single valued functions. Okay, this is the equation for nu. Right-hand side, we have velocity, we have specific enthalpy. Those are physical quantities, those are single valued quantity. Left-hand side, we have nu, which is a potential. So it can be single valued, but it can be non-single valued as well. Okay? So if it's non-single valued, it must be that the material derivative of the cut is equal to 0. So the cut value of this non-single valued function is a conserved quantity. Okay? Now let's look at B and V again. B is given in a Sakurai form. V is a generalized Clebsch form. We dot them. Of course, when we dot them, the 2 terms in the middle, grad chi and grad eta drop because of the dot with the B. And see it from here. Okay. So when you put everything in the cross-helicity, you come out with 2 terms. We have a integral over the flux, d phi is the magnetic flux, which is also d chi the eta, and the other term is also integral of the flux, integral over sigma ds. It's along a magnetic field line. It's integral.
Sure. Please keep the mic closer.
Can you hear now? I have a problem with this device. No problem. Very good. Okay, so what is suggested is a modified topological constant. You see, the flux is co-moving, as Gunnar told us, and nu, the discontinuity of nu is also conserved along the flow. The other term is not. Okay, so we move it to the other side of the equation. So this is a non-barotropic helicity defined just by the integral of the flux times the discontinuity of nu, and this is equal to the standard cross-helicity minus this form. Okay? Now, if you want to write it in a more standard way, you can show that you can write it just the dot product of a magnetic field times a topological velocity. And what is a topological velocity? It's just the standard velocity minus sigma grad S. Okay, this is the topological velocity, and this term is conserved also in non-barotropic flows. Okay. Now, here is a question which we may ask ourselves: why should we care about topological constant? Why should we look for topological constant? And I think one of the answers is that this may affect the stability of MHD flows. Now, what does constants of motion has to do with stability? Well, everybody rides bicycles from now and then, and you know that a bicycle, if you don't hold it, it will fall down, right? But once you go on the bicycle and turn the wheels, then it's stable and you don't fall and you can drive at your pleasure. So non-zero angular momentum is stability. What about other devices which have plasma in them? Tokamaks, stellarators. Can those affect stability? Well, let's look at the following. Obviously, B minus VT square is bigger than 0, and two lines of derivation, you can see that VT dot B is smaller than half B square plus VT square. Okay, so this inequality, if you take the integral, shows you that really energy or a type of energy is bounded from below, and it cannot go, given a certain complexity of the flow, it cannot go below a certain amount. So certain instabilities will be prohibited because of this non-trivial topology, or so we would like to hope. We also have a Cauchy condition. This is another type of lower bound. So a non-barotropic MHD flow with non-zero non-barotropic cross-helicity has another non-zero lower bound on the energy of the flow, and this bound is due to the non-trivial topology of the flow. Since the non-barotropic Rosselicity is a dynamical constant, the energy is bounded no matter what the dynamics are, and thus certain instability are prohibited for a flow with non-trivial topology. But that's not the best thing, because we have a stronger constraint. Consider a magnetic flux tube of a cross-section S in which the magnetic field is almost constant in this tube. So it turns out that you can write a non-barotropic Rosselicity as a discontinuity of nu times the magnetic field times the cross section of the tube. And then you can do all the tricks we have done for just this tube, and you get a local bound from below. We obtain a local bound for the discontinuity of nu in this specific form. So this is much more stringent because the condition we got before was global. It was over all the flow, but this is local. It's per magnetic tube, flux tube. So we know that to achieve fusion, one needs to achieve a stable plasma, which has the needed temperature and density to sustain fusion for enough time. And we know that this is difficult to achieve in Earth conditions, not in the sun, of course. In the sun, it happens all the time. So perhaps a flow with non-trivial nu discontinuity seems to be more stable as the energy of the flow is bounded from below. But of course, all this is true only for ideal magnetohydrodynamics, and we have to say something about non-ideal magnetohydrodynamics. So far, we have discussed only ideal MHD, which does not describe a true plasma since it neglects, among other things, viscosity and finite conductivity. Non-ideal MHD do not conserve topology due to the phenomena of line reconnection. And nevertheless, the fastest processes and most dangerous instability are due to ideal dynamical processes. And this is a quote from Bozer from 2004. A spiky current profile causes a rapid dissipation of energy relative to magnetic helicity. If the evolution of a magnetic field is rapid, then it must be at constant helicity. And Una mentioned the Taylor conjunction. And this will be true also for the cross helicity per unit flux, but this is in a question mark because we are not sure. I'll tell you why. Let's look at the non-ideal case. In the non-ideal case, non-barotropic cross helicity is generally not conserved, and this has to do with many things. One of them is diffusivity, eta, K, which is thermal conduction, and sigma depends on the viscosity. It's a viscosity tensor, so sigma ik with a prime. It's had nothing to do with the sigma we defined before. So many things can happen that will make this suggestion not to work. Of course, it can work in some conditions. If you compare this with magnetic helicity, well, you can see that the non-ideal case is much more simpler because you just have eta times a J cross B in the volume. Okay. Now let me say a few things about Lagrangian variational principles and topological constants of motion. Okay, this we already have. We look at the magnetic flux line, and we define two concepts, which is called load and metage. Load and metage were defined for standard fluids by Linden, Bell, and Katz in this paper proceeding of the Royal Society of London. But we generalize, when I say we, I mean Linden, Bell, and myself, to the case of magnetic fields. So the load, you take the flux of the tube, you take the mass inside the tube, you divide them, and you get the load, and it's a co-moving quantity. And for the metage, which we mentioned briefly, you just go to a certain point, which is co-moving on the magnetic line, and you define the metage at this line. It's the same integral, but you don't go all the way. So from some initial conditions, initial position to some point R. This is also conserved. It's called the metage. It's easy to show that its material derivative is null, and grad mu dot B is equal to rho. So rho is a Jacobian of those three labels, U, mu, chi, and eta. And then you look at the book by Staruk, Plasma Physics from 1994, and he writes the action and the Lagrangian density. He does it only for barotropic flows for some reason. And he writes variation. W is again the enthalpy. And if you take a density variation, which conserves mass and conserves a magnetic field with this displacement vector psi, you get what you need to get. But notice that this is automatically, if one uses Sakurai representation for the magnetic field line and the density Jacobian representation, including the metage. So this is the variation, and you get something like this. You have to assume in Taylor, in this approach, you have to assume things. It's not, doesn't come out of the equations automatically. Okay. Now, let's recall the theorem of Noether, and this is Emilia Emily Noether, born in 1882, and she died in the US in the 1935. She had to run from Germany from obvious reasons because she was Jewish. She was described by Hilbert Einstein as the most important woman in his history of mathematics. And there is a famous theorem that every continuous symmetry group generates conserved currents. So here is the question: what is the continuous symmetry group which generates coarselicity? Okay, now we have the symmetry of Arnold, of relabeling. The fluid element does not care what his name is. You can call it whatever you like. So this is relabeling. And the labels, once you fix them, they are not changed due to the flow. And there's many ways to choose labels, but one of them will lead to the kind of Jacobian, which gives you the density in this form. And this is the same thing. Essentially, we have done the same thing with chi, eta, and mu. And now you can make a symmetry transformation which the Jacobian is equal to 1, and you can make an infinitesimal transformation. This is what you do in Noether theorem. And when you put it in the Jacobian condition, it means that really the divergence in the alpha space of delta alpha k must be equal to 0, and it must vanish on the surface of this space. Okay, so obviously you cannot take delta alpha k equals AK because the surface will be moving. But if you have some label which is cyclic, then there is no problem. So mu goes along the magnetic field line and it is cyclic. And delta chi and delta eta will be equal to 0. And mu is not defined up to a constant anyway. So we have this psi, symmetric psi, which is a partial derivative of the R vector with respect to mu times delta mu. And you can show that this equals to B over rho. And if the Euler equations are satisfied, boundary conditions are satisfied, the variation is null, then you get a Noether current. This must be constant in time. And when you plug this specific symmetry displacement, lo and behold, you get this cross-helicity. And this was in 2 papers. Morad didn't mention the concept of labels, so we had a more complex representation of the symmetry group, but essentially got the same, and also my own paper from 1995. So we have succeeded in finding a symmetry group associated with cross-helicity. The group has a particular simple representation in terms of the variable introduced, but this was done for the barotropic case, right? What about non-barotropic flows? In non-barotropic flow, it's not conserved. So you have to go again, start with a little bit different Lagrangian density. Internal energy now depends on entropy as well. And the conservation of entropy is enforced by a Lagrange multiplier. And you do the calculation again, and you get something a little bit different. But again, boundary condition satisfied, equation satisfied, you have a Noether current. And this is the Noether current for the non-barotropic case. And the symmetry group is the same. And you get this. So you have a non-barotropic cross-helicity through the Noether analysis. Now, what happens if yes, the displacement is not just a uniform translation on the same on every magnetic field line, but different. In each different magnetic field line, we have something different. What will happen then? And here is the answer. Delta mu now you cannot take out of the integral because it depends on space. But you can change the coordinates to the labels, and then you get this in this form. You have integral d chi d eta over delta mu, and this is a line integral going along a magnetic field line with velocity dot magnetic field divided by rho, and this is integral over the mu. So essentially you get a local non-barotropic cross-helicity, which is this I. This is a conserved quantity. And if you do some analysis of what d mu is, because it's just along a magnetic field line, you get this rho b over times dr. dr is the length of this space element. and you get it in a more nice form, which is just a kind of circulation over a magnetic field line of the topological velocity field. Okay? And what does it mean? Well, if the velocity field is in a Clebsch, generalized Clebsch form, you remove the sigma grad S to get the topological form, and you remember that along the magnetic field line, chi and eta are constant. So what remains is again the discontinuity of nu, right? The importance of non-single valued functions in topology. And this is just the non-barotropic cross-helicity per unit of flux, magnetic flux. Okay, so we have cross-helicity, but of course, our group is much more rich than just translation, right? We can do much more things. So let's do something else. Now I would like to put the mu as a constant, don't touch it. And I would like to play with eta and chi surfaces, which can be non-single valued or single valued. I hope I have time to show you some examples. Okay, the equation, the symmetry equation leads to this form, and the solution to this is well known. And you calculate psi for this symmetry transformation, and you get this. Now, that's a general solution. The most simple solution, again, is constant, meaning translation. And the problem, of course, would be if the initial surfaces are, the topology is such that they are closed or not. So let's assume that they are closed. I will show you an example later. And now we get new type of Noether currents, a non-barotropic cross-helicity of the chi type, and a non-barotropic cross-helicity of the eta type. Of course, each suffers a topological interpretation as the cross-helicity does, but it's not a magnetic field now, it's something else, right? And of course, you have to take into account the boundary. And those are the symmetry transformations. Now, those can have effects on stability. Of course, it's obvious in ideal magnetohydrodynamics, less obvious in non-ideal magnetohydrodynamics, but this is the type of lower bounds that we get for all the quantities that we describe. Okay. So we have succeeded in finding the symmetry group associated with cross-helicity and non-barotropic cross-helicity. We have succeeded in finding a local version of non-barotropic cross-helicity using symmetry consideration. This group has a particular simple representation in terms of METAG translations, uniform or non-uniform across magnetic field lines. And those variables are useful also for deriving, that's a question, yes. For deriving a better variation principle, I would like to say that yes. So, okay, this is what we had. I would like to say something about moving, if you noticed in my presentation, from an Eulerian variation principle to the Lagrangian variation principle in order to get those Noether currents. The reason is not fundamental, because you can have Noether currents, as I will show in a second, also in Eulerian variational principles, but the symmetries are much less obvious. And so this is what we got for the Eulerian variational principle, and this is the Noether current which is associated with it. Okay? If you take delta S equals 0, in a symmetry that conserves the entropy surfaces, you get something like this. If you notice that chi and eta are labels, it means that the variation of chi or eta is minus psi grad chi, or minus psi grad eta. And if you plug all this back, this takes this form. And if the variation do not change nu, then you are back to the original Noether currents which we got from the Lagrangian variation. Okay, so I have 9 minutes to tell you about the stationary variational principle. Let's talk a little bit about entropy. A three-dimensional flow allows only 3 labels, of course, but entropy in an ideal flow is also kind of a 4th label because it's co-moving. So we have to distinguish between 2 cases. A magnetic field line lies on entropy surfaces. In this case, the METAG is independent of entropy, and magnetic field lines do not lie on entropy surfaces. In this case, METAG can be made to be a function of the entropy alone, and you get something like this. Okay, so here is the question: how can we represent the physical quantities B, magnetic field velocity and density, in terms of the 3 functions chi, mu, and eta? And of course, we answered those questions for B and rho. B is a Sakurai, rho is a Jacobian. What about V? Now, here is the special thing going on in stationary flows. We don't have partial time derivatives, so div rho V is equal to 0. Chi is co-moving, so V dot grad chi is equal to 0. V is on chi surfaces in stationary flows. And we have a rotation of V cross B equals to 0. And believe it or not, this can be solved. All those equations can be solved, and you can write a solution in terms of V, which is a grad mu cross grad chi divided by rho. It's very easy to show that this solves the bottom equation. Obviously, it's normal to grad chi, and div rho V is obviously 0 because it's just a curve. This is more complex, but it's a few lines of calculations, and you can show that it's correct. Okay, so we solved all the equation of magnetohydrodynamics except the equation of Euler equation. And this is how it looks for a stationary flow. And the solution will be derived from a variational principle. So again, we have an action and a Lagrangian density, and this is the Lagrangian density. It's the standard one. No, nothing. We don't have to add anything. But we plug V and rho and B in terms of chi, eta, and mu. So it's now a functional of chi, eta, and mu. And if you do the variational derivatives, some lines of calculations, those will hold true. This is the variational derivative of V. And you will get the equations of motions in this form, which is essentially the stationary Euler equations. It's just this. So we have managed to reduce the stationary non-barotropic magnetohydrodynamic equation from 8 equations containing 7 quantities to 3 equations with 3 variables. Furthermore, we have managed to represent stationary magnetohydrodynamics as a variational problems in terms of those 3 variables. And for the last 4 minutes, let me mention briefly Aharonov bomb. In 2009, we celebrated 50 years of the Aharonov bomb effect, which was found in 59. This is the logo of this conference. Now, I want to connect it to Renzo talk about non-single valued functions. If you go outside the 50, curl A is null, therefore A is a gradient of function, but flux is not null, and therefore this function S must be non-single valued. And you may know that Aharonov was born in 28th of August 1932. So last week he turned 90. So I would like to say happy birthday to Yakir. And that's the it's an example from his paper of 1959. The gray area is the magnetic flux, and A is calculated, and you can see that S is just the azimuthal angle, which of course is non-single valued, phi over 2 pi. What we have there is a domain that is not simply connected, but can be made simply connected by introducing a cut. So mathematically speaking, the domain is non-trivial fundamental homotopic group. Electron or its wave function do not fill the magnetic field, so it's a non-locality. The potential vector field is a gradient of a non-single valued function. A gauge freedom is not gone, but only limited to single valued gauges. And according to Bohm, okay, my last 3 minutes, the phase of the wave function should be interpreted as a potential of the velocity field. So this is also reminiscence of what we have here in MHD. Okay, so if we look, for example, at magnetic helicity and cross helicity, you can write the magnetic helicity is chi grad eta plus gradient of some function zeta, and B dot A would be this term, and then you get a derivative of zeta with respect to mu times a Jacobian. Okay. This is not true. Okay, so magnetic helicity takes this form, and you have to calculate along a magnetic field line, and you get the discontinuity of zeta. It must be discontinuous, otherwise you don't have magnetic helicity. So you can call it like a magnetic Aharonov bomb effect, and it's as many similarities that you have a domain that is not simply connected, since the internal magnetic field line, the MHD, you always have magnetic field lines which are knotted. So you have one which you can call internal. It's knotted inside the external magnetic field line. The external magnetic field line does not touch the internal flux, yet the zeta function is not single valued due to that line. So this is non-locality, and you don't have to have something which is devoid of gas or lack of air. It's just the fact that 2 lines are knotted. And then the potential vector field has a gradient of a non-single valued function part, and gauge freedom is not gone, but only limited to single valued gauges. And you can write the magnetic helicity is this integral over the flux of discontinuity of zetas, and zeta is the amount of magnetic helicity per unit flux, and it's a conserved quantity. And of course, you have the relevant bounds, lower bounds. One of them is certainly due to Moffat, his paper of relaxation under topological constraints. So you can say that there are two Aharonov-Bohm effects in MHD, maybe more. If you consider also cross helicity, in each case, a magnetic flux induces a phase on quantities that do not come under the influence of the magnetic field directly. Those quantities include the velocity field, an external magnetic field. Those phases quantify two well-known topological conservation laws of the magnetic and cross helicities. One of those phases is useful for introducing a very efficient variation principle for MHD.